closed book and notes, but you should bring your calculator, as I said. There might be one or two numerical problems also, but it will be predominantly analytical. We cannot help that because of the nature of the material covered. Right? So there will be more numerical, so predominantly numerical, at least in the second quiz, and the exam would probably be largely numerical with maybe a little bit of derivation or theory. Right? So from now on it will be a lot of numerical stuff, but this one, it's impossible to avoid this kind of purely theory-based questions. So if not, then we continue with what we were covering. So one point I forgot to mention was this d alpha by dt that comes in the formula. We didn't quite evaluate it. So for alpha, I can write it generally, illustrative of the equation of state. I can write this as alpha equal to 1 plus the whole square. So when I calculate d alpha by dt, the formulas are all there in the book. So you have to, the problem I find is many students just differentiate with respect to dr without forgetting the dc that is hidden there. If you want to do it, you can differentiate with respect to dr and then differentiate dr with respect to t. It is not 1. Because dr is t by dc, so it's 1 over dc. You can directly differentiate this with respect to r, and you will get 2 times 1 plus k, 1 minus dr power half. That is differentiating that square. So then I have to go inside and differentiate with respect to dr. So that would be, this could be 0. So kappa times 1, that also will give 0 for a derivative. So I have minus kappa. Now I am differentiating only with respect to dr. So dr power half is half dr power minus half. The derivative of dr power half. Then we are still left with this. So this would be 1 over dc. And I have the final expression, and you can verify whether this is consistent with that or not. I'll just write down the final expression. This would be d alpha by dt at t equal to t1, which is what we want, can be given by minus alpha t1 evaluated at t1, that is t1 dc power half times 1 t power, which will make it from equation of kpr will be different from ksrk. This is what you will get. So this is being represented as square root of alpha. So that's what you find here, power half. Then I think the rest of the stuff will probably work out. Because this is all evaluated at t equal to t1. So you can easily verify whether this is consistent with what I have worked out. Are there any questions on this? Because I'm going to move on to the next important topic, that of calculating the saturation pressure. So far we have seen the departure functions are there, and we can calculate what is happening between two states as well as there is no phase change. The moment you have a change of phase between any two states, right, we need to know how to calculate. For example, if there is an enthalpy change between two states, and there is an change of phase between. So we are talking basically about working in the gas phase and then moving to liquid phase. We are not going further down into the solid. We restrict our attention to that first. Okay? And so then we have to calculate the enthalpy change associated with the phase transition. Before we do that, we saw from other points also, even to fix the state, whether a particular pressure corresponds to a gas or a liquid state, we need to know the saturation pressure. So that is the basis before we proceed to any other quantity associated with phase change. So we will look at that. Now the criterion for equilibrium, we have already seen is the equality of between two phases, because we are now considering two phases, gas and liquid phase. Right? So P1 equal to P2, P1 equal to P2, and the chemical potential of the two phases are also equal. These are the criterion for equilibrium, the equality of temperature, pressure, and chemical potential. Now, each one of these, as we have seen, can be expressed in terms of any of the four sets of variables, but we choose the temperature and pressure itself as the two variables, which means we are focusing on the fundamental equation associated with the Gibbs free energy or with the chemical potential, which are equivalent in the case of a pure substance. Right? So, then I can write this as compactly as this. T1 equal to T2, I am just calling it equal to T. We have already seen this. T1 equal to T2 is also equal to P, right? My goodness.
Close the door.
So we have this, and so this is the final condition. So we have easily seen that this will yield the saturation pressure for a given temperature. Now I can take this as V phase 1. But to make the problem even more specific, I want to find the saturation pressure at a particular temperature T1, because what this says is an equation in two variables. That means one equation, one variable can be solved in terms of the other. So there's one degree of freedom only. Temperature and pressure both are not independently variables. So this is constrained on the temperature and pressure. Right? So let's say I call this P1 sat. So I want the saturation pressure at a particular temperature T1 that's given to me, right? I'll call that the P1 sat, that is the saturation pressure corresponding to temperature T1. So I'll write this as P1 sat. So if you give T1 in this equation, then I solve for P1 sat. It can be also the other way. I could be given the pressure and then we calculate what is called as a boiling temperature. Usually not called the saturation temperature, but rather the boiling temperature. It can also be there. We will take up the this problem, which is what is handled mostly, but the reverse is also easily handled. Can be easily handled. These equations are the same. Only what variable is specified will differ. Right? So now to make use of the departure function, we already have a formula for the chemical potential in terms of the equation of state. But however, that has the ideal gas chemical potential also. Right? So if I want to make use of those formula, I have to introduce the ideal gas chemical potential. So now, so I subtract both sides by the ideal gas chemical potential also evaluated at the same temperature and pressure. Now I can write this as recognize that this is nothing but a departure function. Only difference is now we have calculated for two phases separately, right? And T1, now it is P1 sat is equal to now if we look at the formula for the chemical potential departure function, now this is very important because we have two formulas. One when T and B is specified, another when T and P is specified. The one where T and P is specified, the two are not equal. We've already seen the complication that can arise because here the equality, the criterion for equilibrium only says the temperature and pressure of the two phases are equal, not the temperature and volume. So the volume will be different, as you very well know, right? So if I look at this formula which we wrote down earlier, maybe we didn't derive it directly, but we did write it down. You will see that this is given by integral infinity to V1. So V1 is the volume corresponding to temperature and pressure. RT1 by V minus this integral is there, and then I also have minus RT1 logarithm. So it's a somewhat lengthy formula, P1 by RT1 plus P1 minus RT1. Go back and check the formula, probably the longest formula among all the formula for the departure functions, right? So this is what we have. Now, if you look at the difference here, well, both of them look like mu minus mu IT. So what is the difference? It is one is V and one is L. Both are evaluated at T1 and P would be here P1 sat. The P1 corresponding what we want is at P1 sat, right? So in this, T1 remains as it is. P1 has to be replaced by P1 sat. What about B1? What happens to B1? So these two are the same in both the formula. There has to be some difference, right? The difference is obviously in the V1. So for the vapor phase, one has to substitute the specific volume of the vapor. For the liquid phase, one has to substitute the specific volume of the liquid. That's the only difference between the two formula for the when applied to the liquid and vapor phase. So the temperature and pressure of the two phases are the same, right? So that is where the difference comes. So let me now write. Even though it's a bit laborious, let me write it. I'll write first the left-hand side, right? Left-hand side would be integral infinity to V1V. The important thing to remember is that first we have only thing that's given is T1, right? And then I said you have to find P1 sat, which we don't know. So that's one variable. So you thought one equation is sufficient to determine one variable, but now I am introducing two additional variables into the equation, V1V as well as V1L, neither of which is known as of now, right? So we'll see how to handle that. Minus RT1 logarithm of P1 sat V1V by RT1 plus P1 sat V1V minus RT1. This is equal to the left hand side This is the defining equation for the saturation pressure. We got now two additional variables that are the specific volumes of the liquid and vapor. Now they subtract one from the other because the two are equal. So I want to bring everything together and write a final equation. This can be simplified considerably. Now this RT1 and RT1 would cancel, right? And let me gather together the easier terms. P1, so first I get P1 sat times P1V minus P1L. If I subtract, so I am taking all of these terms to the left hand side. I have to obviously subtract, right? So then I have minus RT1 logarithm of P1 sat P1V by RT1 minus RT1. This will actually become plus RT1, but I am taking minus RT1 out. So this will be log P1 sat P1V by RT1 minus P1 sat P1L by RT1. Log of A minus B is log of A divided by B, right? So all of these terms will cancel and I will only have P1V by P1L. Now, see, it's important to keep the picture in mind, right? So, let's assume that this is the saturation pressure, and this is V1L, and this is V1V. So here I have infinity to V1V. So I'm going to write this as minus V1V to infinity. The integral A to B is minus integral B to A. That's all I am doing. Same thing I will do here. Minus, but we find it easier to integrate from some lower number to a higher number rather than integrating from infinity to this. Now if I subtract, right, so minus is there. What I am getting is minus integral V1V to infinity. The integrand is the same, right? This is going to be subtracted. So plus integral V1L to infinity, you will get. So what we are actually getting is plus integral V1L to infinity of some quantity minus of the same quantity. So one is from V1L to infinity, another is from V1V to infinity. So again using the integral, we have A to B plus integral B to C, that is equal to integral A to C. On the other hand, right, so if I have integral of some function dx plus here A you can take it to be V1L and C to be infinity. Right? So V is obviously V1V. So you can clearly see what you have here is simply integral V1L to V1V of the integral of RT1 by V minus integral V dV. Are there any questions? This is simple rules of integral. If you are not following exactly, you have to go back and do it. I don't want to sit and write each and every step in an elaborate manner. Right? Basic simple rules of integration. You are very pointed out what those do. You have to sit down and make sure that the signs are taken care of properly to your satisfaction, the way you would approach it. For me, something might be obvious which might not be obvious to you. You sit down, you will work it out. And for some, it may be too obvious, and you may wonder why I am spending so much time on this. Right? So basically, the final answer is what we need, and that is what I have. So you have to make sure that the signs are correct. So now you can see that this is minus RT1 log V1V by V1L. And here I will get a plus RT1 log V1V by V1L. So those two terms will cancel. So basically, I am going to cancel cancel this term with the term that comes out of the integration of RT1 by V from V1L to V1B. Those two terms would be just the negative of each other. I hope you can see that also. Right. So I get now the final striking equation V1 sat V1B minus V1L minus integral V1L to V1B of P bar of V P1 dV is equal to 0. This is the final defining equation. So P1 sat, but it has two other unknowns, V1L and V1B. So how are you going to find those? We need one more at least equation. It might look like two variables are there, right? What is the other equation that has to be combined with this? There's only one equation, we'll see why. Because there are two additional unknowns. One more equation we need. Is that already there? What is that additional equation? Now imagine how we are going to use this equation, because I am given only T1, nothing else is given, right? So I don't know what P sat is, so I have to assume it has to go through an iterative procedure. That looks like a strikingly simple equation. It's a bit difficult to solve. It's a non-linear couple, and I have two other variables, V1B and V1L. So I don't know what it is. The first step is, you write down the algorithm in great detail. First step is you have to assume a pressure, because you don't know, and you know that the pressure is between PA and PB. So immediately it would help if you calculate PA and PB first. Those are the pressures corresponding to the minimum and maximum. Because if I choose some pressure here, obviously I am going to get only one root, real root, as per the figure. So there is no question of vapor and liquid being in equilibrium. So if I again choose a pressure lower than PA, because it cannot be arbitrary, you can choose, but you will find there is only one root. So to make your starting point a bit more rational, you have to choose some pressure between PA and PB. They are going to give you three roots. And of course, middle root has to be discarded, and two of those roots would correspond to liquid and vapor. So once I choose, let us say, some pressure P1 or P0, let's say, initial pressure. So automatically, what I have to do is, I don't know whether this is P1 sat or not, so I will have P0, and then I have to go and solve for V1B and V1L corresponding to that pressure. This will not be may not be, because there is no guarantee the first pressure you choose is going to give you the saturation pressure, right? So I have to calculate that. So I can calculate only one equation, that is the equation of state. So I get three roots actually. Two of those roots I have to take. One is a possible vapor root, one is a possible liquid root. And then integral once I know those roots, possible roots, I can calculate that integral. I have to check whether it is actually being equal to 0. If it is equal to 0, then what you have chosen is correct. So if it is not equal to 0, then we have to choose some other pressure. So it has to go in an iterative fashion. So you can see that one equation along with the equation of state, that's very important. The moment you have chosen P, then the volume corresponding to that, the liquid volume and the vapor volume, are automatically determined by the equation of state. Equation of state is part of the input, right? So we have that. So once I have that, then I have to see whether those three quantities that I have now calculated, three quantities, one which I have assumed, the pressure, the fourth quantity, the temperature is given to me. So I assume a pressure, then immediately the two volumes are determined. So I have to go and substitute it into that equation, right? And check whether the equation is being satisfied. If it is not, then obviously I want to choose another equation between PA and PB. So we'll see how to do that in a systematic manner. So first I give you a geometric, well-known geometric interpretation of this, which is often referred to as Maxwell's equal area rule. So Maxwell obtained it in a slightly different, using a slightly different argument. So to see why it is called as the equal area rule, I have to now represent it geometrically. Geometrically, what the two terms in that equation mean, we now see. Right? So first I have the pressure volume isotherm. You take a look at it at the point, at the pressure at which the equation is satisfied. That's going to give me the saturation pressure as well as the liquid and vapor. So once I know that the equation is satisfied, I automatically determine all three variables. The particular pressure is the correct pressure. The values of the liquid and vapor volume are calculated will be taken to be the saturated liquid and vapor volume. So let me take this. So this is the pressure at which the equation is satisfied. Now can you see what the equation means? So automatically this will be V1L and this would be V1V. Right? So what is the area V1? If I want to represent this quantity, forget even about the area. If I want to represent this quantity, I'm sorry, not this quantity, this one, V1 sat times V1 V minus V1L. Yes, can you mark the area on the figure? V1 sat times V1V minus V1L. Mark it. Very good. We have created exactly. Easy to do that, right? It's a rectangle. V1 sat times V1V minus V1L. That's the area of the rectangle. Is clearly marked, right? So this is the area, the equal area. So that is the area represented by the first term. Now what about this integral V1L to V1V of the pressure P dV? Can you wrote it, right? You wrote it? Yeah. Can you come to the board and attempt? Integral, you know, integral A to B f of x dx is the area under the curve, right? So think about that and see integral V1L to V1V, V dV. Not as complicated as it looks, right? So integral is the area. For now, tell me area under the pressure curve. So mark that with a different shade. It's a V1. No, it is integral. Let me write it here. Integral V1L to V1V. V of V. Anyway, this is all at temperature T1. You don't have to worry about that. So the area under the curve, P versus V, between the limits V1L and V1V. Mark that area under the curve. So look at the curve. The curve is here, right? The curve is this. Area under the curve is what I want you to mark. You can try. Area under the curve. Yes. Differentiate. Don't put the same cross. Put maybe in the opposite direction. Yes, that's correct. Yes. You can't go above the curve. Yes, very good. Yes. That's it. Yeah. So that is fine. So now, if you see everything which has a crisscross, that means it's overlapping both the quantities. But you have to understand, both are positive. V1, I have deliberately written it so that integral V1L to V1V, I'm sorry, V1 sat times V1V minus V1L is obviously positive. So whatever I marked earlier is a positive quantity. Now I have minus the other quantity that Rohit has marked is also a positive quantity because the pressure is entirely above, it's in the positive. The limits are also positive. So that area is also positive. So I have one positive area minus another positive area. So where you have the crisscross, where both shades are there, what has to be done to those areas? It will be cancelled. Everything that is, now I have to only consider the two areas, I'm sorry, the part which doesn't have any crisscross, that is what is left behind, right? So crisscross is here. So the only areas that do not have a crisscross are this area, which is just above the P versus P curve and limited by the P equal to P1 sat line. It's not just above everything. There's the area between the P versus P curve and the line P equal to P1 sat. That's clear. That is actually coming from the rectangle, not coming from the area under the curve. The other area, which is entirely coming from the area under the curve between V1L and V1B, is this area. So you have this minus this. Again, both are positive. In terms of the magnitude, you consider this is the magnitude. Minus this is 0 is what I have. So this is what is y. This is called as the equal area rule. So if I consider the intersection of the P versus P curve and the line P equal to P1 sat, we consider that, right? Now there is a certain area subtended below that line, and there is an area that is created above the line between the two curves. There is a certain area which has as its limits the curve itself and the P equal to P1 sat. The first area which is coming from the rectangle, that is the first term, is this. Exactly P equal to P1 sat and this. That is also P equal to P1 sat and the curve. It is not taking the loop upwards. Right? So those two areas, if we were to call this A1 and this to be A2, that is this alone, not any of this. So those are all getting cancelled. So I can write the criterion itself geometrically as A1 minus A2 equal to C. So A1 is equal to A2 and hence this is called as the equal area rule. You have to know what areas are equal. Equal area rule doesn't give you much insight, but if you know how to construct this diagram, you know which areas to look for. So what it means is that geometrically, if I want to fix the saturation pressure, it gives a way of roughly calculating. So I just move this line so that these two areas are equal. Now you see that idea will be very important when you actually implement the algorithm numerically, because we don't want to do that. We don't want to plot it and move it, roughly and then calculate the area. That's very cumbersome to do. But that's geometrically what you can do. So given the equation of state plot, and if I ask you what the saturation pressure is, you can use that, because optically you can see roughly where the two areas are being equal. So you can adjust it and get an estimate, right? But the fact that this quantity that is here is actually A1 minus A2 will help us come up with the correct algorithm to determine the saturation. You see how it is helping, this geometrical picture is also helping in getting the algorithm right. We see now how the algorithm will proceed to calculate the saturation pressure. So the first step would be to determine, so T1 is given. So what is given? Given is T1 alone, and of course the equation of state. So the substances we assume is given, right? So first step would be to determine PA and PB. Because that will help us fix the initial guess in any nonlinear equation. Initial guess is very important. The initial guess is way off. The solution might not even converge properly. So we want an initial guess. So of course initial guess is always difficult to determine. But based on the knowledge we have, we want to choose the best initial guess. So clearly if I know the form of the equation of state, which I can plot the moment I get T1, and I can calculate PA and PB analytically also. I know that the initial guess has to be between PA and PB. That's a very important information. So I have to choose P0, that will be my initial guess, zero guess you can say, right? So that would be between PA is below, PA less than P0, less than PB. I have to choose a pressure which lies between PA and PB. A good thing is just choose the average, the lack of anything else. Might not always work, but it will ensure that the P0 is between PA and PB. That much it will ensure. So that's all you can do right now. So now we have calculated. Now we have to go to the equation of state and calculate PL naught, PB naught, corresponding to P0, right? Calculate that and check, then check if P0 times PB naught minus PL naught minus integral PL naught dB P of course numerically we can not check whether it is exactly it won't be zero. There's imprecision in any algorithm. So we can say maybe it is less than or equal to some delta, some tolerance you fix. The mod of this, you can use the delta which is positive 0.0001 or whatever you want, depending on how much accurate you want. So we just say that the magnitude of that different, because we don't know that it will be less than 0 or greater than 0. Right? So I can fix the delta as some small number and I can calculate whether the absolute value of that quantity, which is part of the Maxwell, which I want to be 0, is less than or equal to that. Then I get the answer within that tolerance that I have set. Right? So now, obviously, as I said, we don't expect in any algorithm, one important is the initial guess. So we should have, you cannot say just choose some P0 and leave it at that. You have to see whether you can actually get an intelligent initial. The next is the algorithm itself. What you want the algorithm to do. Obviously, it's going to calculate this quantity. So that will be part of it. Now, the condition for the algorithm to stop, because if you want to stop at a certain point, the stop is when I put a question mark, and the question mark is answered. Yes, it is less than or equal to delta. We want to stop, right? That is one. But before that, if the condition is not satisfied for P0, then what do? We have to change the pressure. Again, you cannot say just choose some P1. We have to know how to choose P1. Now the important point is that the geometry would help. Now suppose let us say this quantity, because we want to see whether it is greater than 0. Now we move the numerical part from it. Because we want to see, depends how we adjust the pressure would depend whether on the quantity we have calculated is greater than 0 or less than 0. For the tolerance, I only look at the magnitude. How I am going to adjust the pressure, what will be my P1, will depend on it. Now suppose this quantity that I have calculated is greater than 0, then looking at the diagram, right? So how would this diagram now look like? So now I am going to draw a line so that this quantity is greater than 0. So which area must be greater? A1 must be greater because this whole thing is A1 minus A2. That is very important to keep in mind. Because I can also write this equation as P d1 dv minus P1 sat. But I haven't written it like that. We stick to one form. And so A1 must has the, and you should also know which is A1 and which is A2. So clearly, if this is greater than 0, then it would correspond to something like this, let's say, to make it very clear. This would clearly correspond to a case where the quantity that I have written here is actually greater than 0. Now, it's very easy to see from the diagram, do you want to reduce the pressure or increase the pressure? Tell me. Clearly we want to reduce the pressure. So if this is true, then P of 1, right, would have to be less than P0. You can clearly see we have to bring the pressure down to make A1 become closer to A2. A1 is much greater than A2. By the same argument, if this whole quantity is less than 0, then clearly we get that P of 1 must be greater than P0. Easily construct a similar diagram and convince you. So that is very clear. Depending on the quantity which I calculate, here obviously numerically it will be whether it's the first step is of course to calculate that the absolute value is less than a certain delta. If it is not, then we have to look at the actual value, not just the absolute value, because that will determine whether you want to increase the pressure or decrease the pressure. Right? So how we want to do it is also then becomes an important point. Increase the pressure means you can say P of 1 is equal to P0 minus some delta. That will ensure, because we keep the same delta for all possibilities. It can be greater and less by, it can be greater than 0 by a large amount. So we want to reduce the pressure. This is one way of doing it. And here if I say that, I will say that P plus delta. That may be an inefficient algorithm because for whatever may be the depending on how far it is away from 0, we want to adjust the difference in pressure also accordingly and not keep the same difference for all possibilities. Because it can be 100, it can be 0.1 also. Right? So we cannot have if we have an algorithm which says that P of 1 equal to P0 minus some small quantity delta for all possible values of this quantity which is greater than 0, then the algorithm might not be that efficient. It might converge very slowly. Definitely converge. Because if it is much greater than 0, then we want a corresponding adjustment in the pressure so that it is pushed towards the correct value. You cannot say all the time I will give the same increment or decrement. Right? So we'll see in tomorrow there is no class because we have a quiz and there will be an exchange of slot. We'll meet again on Wednesday to see how to complete this algorithm.